Okay, hello everyone, and welcome. Thank you for joining us. Before we get started, I'm curious to know how many of you have faced performance or cost challenges in Amazon RDS? If you could raise your hands. Okay, so looks like everyone here, which means that you came to the right place, because in today's presentation, we will explore tips and best practices on how to boost performance and reduce costs in Amazon Aurora and Amazon RDS. I'm Penny Dibask. I'm a senior database solution architect at AWS, and I will be joined later by my colleague Tim, who is a senior principal technologist at AWS. I assume many of you are already familiar with Amazon RDS, but just to level set, it is a fully managed relational database service. With Amazon RDS, you're able to spend time innovating and optimizing your applications rather than focusing on the operational database management tasks like upgrades, backups, provisioning, etc. It supports commercial engines like Oracle, SQL Server, and DB2, as well as open source engines like MySQL, Postgres, MariaDB, and Amazon Aurora. Amazon Aurora is quite unique because it is a cloud-native database engine, which was designed to provide you the enterprise-grade security, availability, and reliability of commercial-grade enterprise databases with the simplicity and cost-effectiveness of open-source databases. And due to some of Amazon Aurora unique features and characteristics, it is actually the fastest-growing service in the history of AWS, with hundreds of thousands of AWS customers who use it today as the relational database. I would like to start to dive a bit deeper and talk about the various RDS cost dimensions. There are costs associated to every RDS cluster, and these would be compute and storage. There are additional costs which are very common, and we find them in most of our customer workloads, and these would be backup, data transfer, and IOPS. There are also costs which really depend on your specific application use cases and which database features you use for your applications. In today's presentation, we will walk you through some of the most common cost dimensions and how we address those and how we optimize those. And the way we will do that is by using examples from a company named Any Company. This is just a made-up customer journey, but it does represent some of the most common customer challenges that Tim and I often see in our day-to-day with customers like you. So to give some context about Any Company empowers e-commerce sellers with generative AI to turn every product into a bestseller. Their key AWS services are Amazon EKS for the application layer and Amazon RDS for the operational database layer. Any Company is a fast-growing, successful startup, but they're still an early-stage startup. And one of their challenges is balancing cost and performance as their scale. And this is a challenge that we typically help customers tackle. So the way we will do that, we will walk you through the journey with Amazon RDS, and then in the second part of the presentation, Tim will walk you through a similar but different journey, this time with Amazon Aurora. So you will also learn about the similarities and differences when it comes to RDS and Aurora in terms of performance and costs. There are three key dimensions that I would like to talk about and focus on in today's presentation when it comes to cost: compute, storage, and backup. So let's get started with compute. And I would like to introduce Any Company's first challenge. Any Company started with an instance type R6G extra large. And in the beginning, it worked just fine. Everything was working smoothly. However, as customer adoption increased, they noticed that the CPU utilization metric in CloudWatch occasionally spiked to 100% utilization. And that made an impact on the reliability of their solution. Some customers even complained about slowness and timeouts. So the obvious question that many customers ask us, what is the right RDS instance to use? And that could be a tricky one because there are so many RDS instance types that you can use. And this is a common question we get from customers. So we need to make sure we find a solution that is both performance and cost conscious. With AWS, you have plenty of options. So burstable instances are great for smaller or variable workloads. General purpose suits CPU-intensive applications. Memory-optimized instances are great for memory-intensive applications. And Graviton, which is based on ARM architecture, provides improved price performance compared to x86 counterparts, making them ideal for various workloads. By the way, you see here Graviton 3, but we actually announced recently Graviton 4 support for Amazon RDS. So now we also have RAG and MAG support for Amazon RDS. Now, you may ask about what are the best ways to find the right instance to use, because there are so many options. And I would like to show you which tools any company uses before they make right-sizing decisions. And let's start with monitoring tools. When it comes to monitoring, there is the obvious service, Amazon CloudWatch. This is AWS' main monitoring and observability service. It allows you to monitor, visualize, and alert based on dozens of instance-level metrics like CPU, memory, network, and disk-level utilization metrics. When you need to dive deeper into more granular operating system-level metrics like Linux huge pages and swap activity and OS process list, this is where RDS enhanced monitoring comes into play. And when it comes to deep dive database level monitoring, including visualization of SQL statements and wait events, this is where RDS Performance Insights is the right tool to use. And speaking of RDS Performance Insights, what we have found is that many of our customers told us they found it very effectively and efficient to diagnose even the most complex database bottlenecks, because it helps you visualize, drill down, slice and dice the activity by various dimensions, like wait events, SQL statements, application servers, etc. It supports all of the Amazon RDS engines. So this is a very useful tool that we typically recommend customers to enable. Now, we also found that many customers use performance insights prior to right-sizing decisions. So when we find a database load chart that looks like this, where the number of vCPUs in the instance is much higher than the database load, we know that this is a potentially oversized instance, so we might have cost optimization opportunities. On the other hand, when we look at the load chart and we see that the number of vCPUs of that particular instance is lower than the actual workload and the actual database load, then this is a potentially undersized instance. So we will need to either tune the application, the database, the SQL statements, or alternatively, right-size the instance. Many customers, and I'm sure some of you could resonate, told us that you find CloudWatch and Performance Insights useful when it comes to right-sizing decisions. But you also told us loud and clear that you need more help with automated recommendations at scale. Some of you have dozens or hundreds or thousands of instances, and you need more automated recommendations at larger scale. And this is why a few months ago, we listened to your feedback, and we actually announced AWS Compute Optimizer support for Amazon RDS MySQL and Amazon RDS Postgres. So now we can help you identify the right instance size for your fleet of instances. In this example, in this screenshot, you can see a recommendation to move from R6G, which is based on Graviton 2 generation, to R7G, which is based on Graviton 3 generation, that provides improved price performance. And using the right tools and using AWS Compute Optimizer helped us to solve the first challenge of any company. And by moving to R7G extra large, which is based on a newer Graviton generation, they managed to achieve 27% price performance improvement, and that allowed them to provide a more steady state and stable workload for their customers. So they provided an improved price performance. And this is also a great example of taking advantage of the latest Graviton innovation, not only to boost performance, but also doing so in a cost-conscious manner. The second challenge is noisy neighbors. So in the case of any company, the performance started to degrade once internal customers, who are essentially data analysts, started to query the database for reporting purposes. They needed to build some dashboards for the executive leadership team, and those reporting queries made an impact on the core customer application. So this is a classic case of noisy neighbors. And this is a common scenario when we see competing workloads on the same database resources, and we need to find a way to effectively separate those or manage them in a more effective way that they don't interfere each other. So the obvious approach or the traditional approach is to scale vertically by right-sizing the instance and moving to a larger instance. However, with read replicas, we have more flexibilities. So we can create up to 15 read replicas. Each one can be in different size. And by doing so, we can eliminate the noisy neighbor issues and ensure higher throughput for our application. You may ask about the cost differences between vertical scaling and horizontal scaling. And the answer is that it really depends on your specific application use case. Each workload is unique. But in the case of any company, scaling vertically from R7G extra large to R7T to extra large actually doubled the compute cost. So they decided to go with horizontal scaling using read replica. And they found that using a smaller read replica, R7G large, actually managed to address their reporting queries very effectively and very efficiently. And that provided a more cost-optimized approach for this noisy neighbor issue. And by the way, you may notice some price examples here. We are using pricing from North Virginia. These are on-demand pricing. Just be aware that with Amazon RDS, you have the option to use reserved instances. So if you can make a longer-term commitment for 1 year or 3 years for your steady-state workloads, you could actually achieve significant discounts. But for simplicity's sake, we will be using on-demand pricing from North Virginia in this example and all the remaining examples in this presentation. Another alternative to address the issue is to cache frequently accessed data like SQL result sets using Amazon Elasticache. This enables to provide faster performance and in many cases at a much lower cost compared to other alternatives. Now, the way it works, there are several caching strategies, but one common one is every time we write to the database, let's say we insert or update a record, we also simultaneously update the cache, the Amazon Elasticache. And once we need to read the data, we can do that directly from the in-memory database, and that provides improved performance. However, using Elasticache to cache frequently result sets, it doesn't meet all use cases and all workloads. There are some situations where you have very unique ad hoc dynamic filters, and in those cases, using Elasticache doesn't necessarily provide the best outcome. So in this specific use case for any company, because most of the workload, most of the reporting queries are dynamic, they're ad hoc, they're based on unique queries, in that scenario, they decided to go with a different route, which is offload queries using read replica. And using that approach, they managed to achieve an overall 50% improvement in the core customer-facing application performance in the API, essentially. So this is a great way to see how using read replicas by offloading read-heavy queries, you can make sure that you eliminate noisy neighbors while allowing both to run smoothly. And now I would like to talk about the second dimension, the second cost dimension, which is storage. In Amazon RDS, you have a range of EBS options to match your performance needs. GP2 ties the number of IOPS to the amount of allocated storage. So as you allocate more storage, more gigabyte or more terabyte, you will benefit from more IOPS. GP3, on the other hand, allows you more flexibility, so you can allocate IOPS and throughput independently of the storage size. So again, more flexibility. However, both GP2 and GP3 are best suited for development and testing environments, and also for medium-sized workloads. When you need to make sure you have a mission-critical applications that require consistent low latency, this is where IO1 and IO2 Block Express are the go-to options, with IO2 being more recommended due to its improved durability, throughput, and low latency. So just to understand the comparison, with IO2, you get 5 nines of durability, 99.999% durability. This is 100 times more durable than IO1. You also get sub-millisecond IO latencies. This is the only EBS option in Amazon RDS that provides you sub-millisecond IO latency. By the way, IO1 and IO2 are priced the same. So if you are using IO1 today, you can and you should consider moving to IO2 to benefit from improved performance, durability, without additional cost increase. So definitely recommended to move from IO1 to IO2. It's an online operation, but as we always say to our customers, please test that in a pre-production or non-production environment before you do so in production environment. So back to any company now for another challenge which revolves around EBS IO latency. As their database scaled, they reached EBS IOPS limits. And that caused their IO latency to spike from 2 milliseconds to 500 milliseconds, which is a significant performance hit. This is a scaling issue we occasionally see where high IO demand could lead to IO bottlenecks and IO latency issues. So we need to find a solution. And sometimes, in addition to instance right-sizing, we also need to do storage right-sizing. And the requirements from the customer DevOps team, from any company's DevOps team, was very clear. We need sub-millisecond IO latency. This is a super mission-critical application. And similar to all the other challenges that we're talking about in this presentation, using the right monitoring tools, we managed to easily identify the bottleneck. So here we can see RDS Performance Insights metrics dashboard, clearly indicating that there is increase in both number of EBS IOPS and the IO latency, which, as mentioned, increased to 500 milliseconds. So the solution here was using storage right-sizing. In our case, moving from GP2 to IO2 Block Express was the right move because that provided the customer sub-millisecond IO latency. Using tools like CloudWatch, Performance Insights, and Compute Optimizer help you understand when and where adjustments are needed. And now for the challenge number 4. The fourth challenge is around slow reporting queries. So the customer, we talked about internal customers, data analysts to run reporting queries on the read replica. And what they do, they essentially run these complex SQL queries, which include a lot of joins and order by and group by. And what we found is that the average load time of those dashboards is around 10 seconds. Executive leadership team said, we can tolerate up to 5 seconds. We started to dive deeper into the performance issue, and what we have found is that these complex SQL queries generate a lot of temporary objects. Database systems like Postgres try to perform operations in memory for optimal performance, but in some cases, in some situations, when there is not enough memory for those operations, they actually write temporary objects to disk, and in our case, to EBS. And that could add latency, especially for large data sets and complex queries. So one way to address this issue is using a great feature, which I highly recommend to most of my customers who face this issue of temporary objects being written to the EBS, and that's called RDS Optimized Reads. RDS Optimized Reads essentially provides you local, fast NVMe SSD that is targeted especially for that use case. Instead of writing those temporary objects, which are needed to store intermediate results of sort or group for queries, they store it in these local NVMe SSDs. So that requires you to use instance that supports this type of local NVMe SSD, like R6G or RID. And in our case, by using optimized reads, we managed to address this issue. So we can see here a cost example. Any company could have chose to scale vertically and move to R7G extra large for their read replica, and that would double the compute costs. However, they decided to use optimized reads with the latest Graviton generation that currently supports optimized reads, which is R6GD, and with a smaller instance type, R6GD large, and that provided them the performance they needed. So they achieved 2 times faster execution time for their queries without increasing the expense of their infrastructure significantly. In fact, the difference between the original instance type to the new instance type, which is based on optimized reads, was less than 10%, and yet it provided 2x performance for their reporting queries. So if you are facing issues where a lot of temporary objects are being written to the disk because of complex queries that need to store intermediate results for sorting or querying for group by or order by operations or join operations, RDS optimized reads could be a great candidate for your solution, for your problem. And now I would like to talk about the last cost dimension, which is backup. RDS offers two types of backups, automated backups and database snapshots. Automated backups include daily EBS snapshots, and in addition to that, they also store transaction logs in S3 every 5 minutes. The benefit in automated backups is that it provides you for a granular point-in-time recovery in your retention period. And the retention period could be up to 35 days. 35 days is the maximum. Database snapshots, on the other hand, can be taken at any time, and you can retain them until you delete them. So there's no expire date for those snapshots. So that provides you more control over long-term backup management. And this leads us to the last challenge of any company, which is high backup costs. Any company had a backup retention of 1 month, which is pretty standard for companies, 1 month of backup retention. However, a closer look at the customer requirements actually revealed that they only need 1 week of data to be restorable, and any data older than a week needs to be accessed for compliance queries only. Doesn't need to be restorable, just needs to be accessed for compliance queries only. So we had a requirement to reduce backup costs dramatically. And there are several cost-efficient ways to handle long-term backups. One way is using snapshot export to S3, which could be either full or partial. So we can do that for the entire database or for specific schemas or tables. And then we store it in Apache Parquet format, which is ideal for storage and querying using tools like Amazon Athena. It is a compressed format. Another alternative would be to use logical backups using native database tools. So for example, with Postgres, you have pgdump. With MySQL, you could use MySQL shell dump. So these are different ways to provide cost-efficient long-term backup methods. And the benefit in both of these cases, whether it's snapshot export to S3 or logical backup to Amazon S3, is now the data is stored in your customer-owned bucket. So you have full control over the storage class. So for example, you could define it to be S3 standard, which is ideal for frequently accessed data. Or alternatively, if you know that the access pattern requires less frequently access to that data, you could use S3 infrequent access or even S3 Glacier. So it provides you more flexibility around how you store your data, whereas with native RDS backups, like automated backups and database snapshots that we mentioned earlier, you don't have control over which S3 storage class you use. So this gives you that flexibility. Now, using this approach, we managed to reduce cost of backups significantly. We can see here the original backup cost, which uses the 30 days of automated backup. Let's assume the database size is 500 gigabyte, and we have 100 gigabyte of daily EBS block changes. We assume the initial snapshot is 500 gigabyte, and it's free because AWS provides you up to 100% of your database size as free backup storage cost. And then we charge for each incremental snapshot. And you can see that each incremental snapshot is 100 gigabyte, represents the daily block changes. Alternatively, with the cost-efficient alternative, what we can see here is that we only use 1 week of automated RDS backup, and the remaining data, we use the S3 snapshot export approach that we just mentioned in the previous slide. And that provided significant cost reduction. And to be more accurate, that reduced their backup cost by 30%, demonstrating how efficient backup data retention could lead to significant savings while still maintaining compliance, access, and data retention requirements. Now I would like to pause for a moment and ask you, what do these three pictures have in common? So we can see here flashlight, radar, and magnifying glass. Exactly. They all provide visibility. So these are all tools which provide visibility and detection. And the reason I show it is because when it comes to database performance and cost, you can't fix a performance or cost problem that you can't see. So we discussed about some of the tools like CloudWatch, Performance Insights, Enhanced Monitoring. And these tools are great for our customers, and any company uses them throughout their entire journey, as you saw. However, any company also raised some challenges with the traditional monitoring tools AWS provides. And maybe some of you could resonate with those challenges. So I would like to talk about those challenges and show you what we've built to address those. So we have an interesting announcement coming soon. The first challenge is that while Performance Insights is very useful for deep database diagnostics, the information is always presented at instance-level view. You can switch between instances, but you never see the full picture because you always see one single instance at a time. And when you think about any company's journey, they started as an early-stage startup, but once they scaled and became bigger and had to manage dozens or hundreds of instances, that problem became very relevant for them. Another challenge is, as you know, in AWS, we have a lot of data, performance data, traces, logs, scattered around so many tools. So for example, CloudWatch and CloudWatch logs, RDS Enhanced Monitoring, RDS Performance Insights, RDS Events. Many of our customers asked us to provide a centralized telemetry so they can have a true single pane of glass. And lastly, many customers told us that they would like to better understand application context, and particularly correlation between application API and database performance. So we've listened to your feedback, and today we are very happy to announce CloudWatch Database Insights. With CloudWatch Database Insights, with this new announcement, we consolidate all of your database monitoring into a single unified view within Amazon CloudWatch. So you can define a fleet of instances by specific tags or specific instances within a region. And then once you do that, you get a heat map that shows you instance summaries so you can understand where are your bottlenecks based on various dimensions like database load, database alarms, and different metrics. So with this launch, we support both Amazon Aurora Postgres and Amazon Aurora MySQL with additional RDS engines coming in the future. So stay tuned for that. Also, another innovation with this announcement is that for the first time, once you dive into a specific instance, you can correlate all the traces and log data and wait events because now you have a full, out-of-the-box, native centralized telemetry. And lastly, maybe some of you are familiar with CloudWatch Application Signals, which is an application performance monitoring solution. It's an APM tool. And CloudWatch Application Signals allows you to use CloudWatch Agent and AWS Distro for OpenTelemetry to capture performance and trace data. Many customers told us, we need a better together story. We need to better understand the correlation between database performance and application performance. So we need to see the dependent API calls and dependent services that are associated to any database bottleneck. So now, with CloudWatch, you can do that. With CloudWatch Database Insights, we provide you this visibility into dependent API calls for each database bottleneck. Last but not least, many of you that use Performance Insights, you're probably familiar with looking into a specific instance and diving into a problematic SQL statement. You're looking at the metrics or statistics like number of executions, number of temp reads or temp writes, number of page reads or page writes. And you maybe see a number, but typically the number is aggregated across the time period that you selected. So looking at the last week and seeing that this specific statement took 10,000 execution is useful, but it would be much more useful to see the trend over time. So now with this launch, we also provide you the ability to see trends over time for each SQL metric and each SQL statistic. So it's not only seeing a total number, which could be helpful, but doesn't tell you much. Now you could see how it behaves over time. So just to summarize, you can't fix a performance or cost problem that you can't see. So you should leverage the latest monitoring innovation like CloudWatch database insights and be more proactive. And definitely any company uses those tools in order to address their challenges. And speaking of any company, I would like to quickly make a recap of their RDS journey before I hand it over to Tim. So we started with the issue of increased workload due to customer adoption rates. We solved that using instance right sizing and specifically by using Graviton, the latest Graviton innovation, and that provided improved price performance. Later, we have the issue with noisy neighbors, and we solved that by offloading the reporting queries into Read Replica. So now both the core customer application and the reporting queries can run together smoothly without interfering each other. Later, we had the issue of I/O latency. And by doing storage right-sizing, by moving from GP2 to IO2 block express, we managed to achieve sub-millisecond I/O latency. Later, we had the issue of slow reporting queries. We noticed that these queries are complex. They run a lot of joins and order by and group by operations. So we identified and create a lot of temporary objects on the EBS. And by moving to RDS optimized reads, we managed to improve performance by 2 times. And lastly, we had the issue of high backup cost, which we solved by using cost-efficient long-term backup methods like snapshot export to S3. And now I would like to hand it over to Tim, so you will learn about a different but similar journey, and this time with Amazon Aurora. So Tim, stage is yours.
You clapping for me or for Penny? All right, button. Come on, button. All right. Hi, folks. My name's Tim Stokes. I'm a Senior Principal Technologist with Aurora here. Thanks to Penny, you know all about RDS. And now I'm going to tell you kind of a similar story, but with a whole different punchline with Aurora. So, excuse me, we're going to start again with this any company journey. But this time, in their fictional startup, they're deciding to begin with Aurora instead of beginning with RDS open source, okay? So Aurora is a relational database management system built for the cloud with full MySQL and Postgres compatibility. Penny told you a bit more about that before, so I won't dwell on it. The idea here is it gives you 5 times the throughput of standard MySQL and 3 times that of Postgres, right? And it gives you a whole bunch of resiliency down in the storage layer. That's what's magic about Aurora that's different to RDS. It gives you some different trade-offs, and they come across differently when we're talking about price and performance, all right? But just because any company, the fictional one, chose to do this at the beginning, doesn't mean you have to choose to do this for real at the beginning. You can always migrate between RDS and Aurora using AWS Data Migration Service if you wish, or some of your own tools, okay? You can do this whenever you like. Cool. So just like with RDS, we've got these 3 cost dimensions that we need to get through. So we're going to go through them here. But like I said, Aurora talks about the storage a lot more. So what I'm going to do is break the script and kind of do storage in the middle first, because it's more interesting for Aurora. Aurora storage, you have to learn a little bit about how it works first before we can talk about the rest of it. So it disaggregates the storage from the head node, right? It's down in that bottom Aurora storage green box at the bottom there. You can see it's spread across 3 availability zones. It's made up of a large number of storage nodes. Here I've just got 6 because I can't draw that well, but there's a whole bunch of them in each availability zone. The little coloured boxes indicate other people's data. These are multi-tenant storage nodes. It's a multi-tenant storage fleet. So when you do a write, Aurora makes 6 copies across all those storage nodes. You're only paying for one of these copies. It's the first time I've talked about payment. You're only paying for one of these things, but you're getting 6-way, I can't even do it with one hand, 6-way durability across 3 AZs. So what that means is that we can lose availability of a whole AZ's worth of storage nodes and one more storage node in your volume, and we don't have any durability or availability problems. That's all out of the box with Aurora. That's what you're getting when you're paying for Aurora storage, okay? But how does this impact performance? We'll talk about that, okay? So we've got some challenges, different challenges though for this company, right? So some customers are bursty, right? We've got these regular customers off to the top corner there, and now we add some bursty customers. That's a bit of a challenge, right? So maybe this can happen when their geography wakes up, or maybe some Taylor Swift goes on sale or something like that, right? Maybe whatever your any company does has this kind of similar pattern, right? So Aurora will take care of some of that stuff for you already. We don't have to worry about it quite as much, not quite so much hand-holding. But with this flexibility comes maybe a bit of a problem in that it can lead to I/O cost surprises, right? Just because you've got practically infinite I/O on the back end doesn't mean you maybe want to pay for it. So we have these challenges, right? What we want is to have improved cost predictability for our Aurora database cluster. And what we'd really like is for that I/O cost to reduce as well, okay? So we'll talk about how we're going to do that. So Aurora is pay for what you use with respect to storage and other things too, right? With storage, it's storage size and it's I/Os. So first we'll talk about storage size, right? So this is billed per gigabyte a month, just like a lot of other AWS services are. And AWS is going to expand that volume when you need it. You're not doing it by hand. It's going to contract it when you no longer need it. You can see what's happening. You can look at that CloudWatch metric, volume bytes used. And some of this is in your control. You can, if you're in Postgres, you can run some vacuum to keep your size under control. You can configure auto vacuum, right? So now let's talk about I/Os. Every database page read operation counts as one I/O here, right? Doesn't matter which database engine you're using. And the writes, because of the way Aurora works and the database engines work, they're billed in lumps of 4 kilobyte units, okay? Because they could be of varying sizes. They get batched together. Excuse me. So in Aurora, they're billed per 1 million requests, both of these things. So the number of I/Os you can make is scalable. So it's not provisioned like what Penny was talking about before. Just as long as you can drive the I/O through the instance, we're going to give you the I/O, okay? That's how Aurora works. So here also you can see I've just got one Aurora instance at the top. Now, we'll talk about it a bit more, but I'll spoil the surprise and say that you can have multiple of those replicas at the top. As they're doing I/O, it all, for the purposes of price and performance, it all works the same. They share the same storage, they share the same billing methodology and the same performance methodology. Okay? Next one. So now we're going to do a little example here, just like we did before. So we start at 100 gigabytes of volume, and we're growing at 100 megabytes per day. So they can look at this in CloudWatch, any company if you like, right? So this will show their instance cost there. You can see we're using an R6G.X large. We're doing it for 30 days. Times some rate gives you about $370. We have the same proviso at the bottom there about North Virginia and on-demand instances. I'll do the same thing that Penny did for consistency, right? And their base load reads and writes is 600 I/Os per second. Okay, so what does that look like? That looks like 600 times 30 days, 24 hours and all of that, comes out to about $207. Now storage cost, that gigabytes cost per month, you can see a bit of a complicated maths there, it's not too scary. 10 cents per gigabyte month, counting out that base size, plus the growth, plus the growth, plus the growth, gives you about $300 a month, okay? So the problem comes for this customer when we introduce this burst of load, right? So there's a big burst. It's 15,000 I/Os per second. You can see this again in the volume right IOPS CloudWatch metric there. So we do the same maths again, and we look at what the I/O cost looks like for that burst, and it's another $648, right? That's pretty significant. And in this case, it's not very predictable. We don't like that, okay? So how are we going to deal with it? What we're going to do is we're going to introduce this thing called caching, right? So I'm sure it's not very unfamiliar to people in the database speak already, right? So we're not trying to avoid provisioning a large number of I/Os like we did in Penny's talk, right? We're instead trying to reduce I/O cost by insulating against those bursts. So here we can scale up the instance, right? instance is getting bigger. And we don't have to do so many reads anymore because the cache is getting bigger. We scale it up again, a few less reads have to go through. Scale it up again, cache gets bigger, less reads. Right? So you can see the correlation here between more cache, less IOs might save some money there. And your performance probably improves too. So this is a good trade-off to make. So this is a valid technique, right? But it might not be the best solution for any company just because of their balance of burst versus regular IOs. So we'll dive into another solution, see what happens. All right? So what we're going to do is we're going to leave the instance size the same in our example now, just so that my example can continue through. All right? So Aurora's got a different option here that we can use. It's called Aurora IO Optimize. This is a pricing option. So this is different to standard, which is what we've been talking about already. With IO Optimized, there's no charge for read and write IO operations, right? 0. We no longer worry about that. You only pay for your database instance and you pay for your storage gigabyte months, just at a different rate, okay? This makes it really easy to predict the amount of cost that you're going to have because it doesn't have this variable component inside it, right? It also can give you up to 40% savings. If your IO charges exceed about 25% of your bill generally, that's where this will start to break even and become positive for you, right? I don't want you to choose it if it's not positive for you. So this is the rough rule of thumb. You can use the pricing calculator to find that out for yourself. It will also increase your throughput and reduce latency. It's not just a pricing option. We're actually doing different things in the storage here too. And any future performance optimizations will definitely go into IO optimized first, right? You can switch your cluster to IO optimized just with a single click. You can flick it on and off. Doesn't take any downtime. You can turn it on whenever you want. You can turn it off once a month. If you give it a try, it doesn't work out for you for any reason, turn it back off again. It's up to you, okay? No downtime, no failovers, none of that. All right, so let's see that cost example again that we just did, but this time we'll use IO optimized, right? So the conditions are the same. The gray bits they're no different than before, so we don't have to pay attention to them. So we use the instance cost here, right? The instance is billed at a different rate, but all the other numbers are the same. Comes out to about $486. Storage size, all the parameters are the same, so you still grow the same amount. You just end up with a different cost multiplier, $675 roughly. Right? Now your storage IOs, the regular base load ones and the bursty ones, they cost you nothing because you're using IO optimized. And they're probably going faster too because you're using IO optimized. So adding this up, trust my maths or check me later, that's about a 28% cost saving. This is pretty typical. If you've got a fairly IO dominant application, IO optimized will save you money. We want you to switch to it. All right, so our solution to this first challenge, we seamlessly switched over to IO optimized, just that one click in the console or CLI, and we were able to improve our predictability. Now we know what our bill's going to be, and we save some money too and improve some performance. Cool. Challenge number 2. We've got different internal customers at the back end here, right? They might be running read-heavy reporting jobs, end of month, that kind of thing. I'm sure you've got a similar idea in most of your companies. So what these can do is that they can cause issues with performance because they can thrash out the buffer pool inside your node, and they can impact the performance of the other queries too. The front-end queries, that's where our money comes from, right? As a company, we don't want that. So what we want is a way to reduce the impact of these back-end jobs on the front-end queries. And we'd also want to reduce the impact of these back-end jobs. And we'd like to improve the overall performance, right? And remain cost-effective. That's the idea. So how are we going to do it? Here's this picture again. We have an Aurora instance. We have that shared storage layer at the bottom. What we're going to do is we're going to add another instance. We just add another instance to this cluster. They see the same physical storage. We're not copying storage here. We're not migrating anything. Here we've got 2 read replicas, and I'll put them in different AZs, but you can do whatever you want. You can pack them in the same AZ. You can make more than 2. You can make up to 15, actually, in Aurora. And they can be different sizes, too, the same size here. All right? There's no effect on data durability. This is not a durability question. That's all in the storage. So there's only ever one writer node, right? And one of its jobs is to keep all these replicas up to date as the transactions come in. So it's not perfectly synchronous, but it's milliseconds lag, right? So you don't really have to worry too much about having inconsistent results. All right? So what this can do is we can It's also a failover target. Each of those replicas is also a failover target. So we can think about this as a performance improvement tactic, but also it's improving your resiliency by giving you failover targets, okay? So you can balance cost, performance, and availability on the same scale, right? But for any company, it's got a pretty big working set. So maybe we'll say this set of trade-offs doesn't make much sense. Maybe it's not economical. So we'll go and look at something else, okay? Optimized reads for Aurora Postgres. So Penny talked before about optimized reads for RDS. This has got the same name, same kind of idea, but it's a little bit different. So we still have the NVMe SSD in your node, the R6GD, for example. And just like in RDS, we can use that instead of EBS for storing temporary data, okay? That's the same as RDS. Penny explained it before. I'm not going to touch on it, but it's still a really good idea to do it for that reason. But it also gives you this thing called tiered cache. Tiered cache lets you expand your buffer pool out of memory onto that SSD as well. And so that can give you up to 8 times performance improvement on some of the queries if they're particularly read heavy. And it might work out more cost effective because obviously it's not quite as fast as the memory that you're replacing it with, but that instance is a lot cheaper. So it might balance out. Just have to do the sums on your working set. Right? So let's see how it works out for these guys. Remember, you can do this by just switching your instance type, which is just a quick failover operation in Aurora. You have to choose one of those instances with a D on the end, and that's it. And you have to be using IO optimized like I talked about before. There's no other settings for you to turn on. All right, so we'll work through a cost example of using optimized reads. So this is any caching solution is going to depend on how cacheable your workload is, right? So we have to have a discussion about working set, how big your queries are, how likely these pages are to be read again. You have to have this idea, same calculus you're doing with an in-memory buffer pool, you're going to do the same calculus here. So you can estimate this by looking at a couple of CloudWatch metrics if you're unfamiliar with this, so I hope that you get into that pretty quickly. So we've been using an R6G xlarge, in the example so far, just so you remember. So what we're going to do is we're going to switch that to an R6GD.xlarge, right? And going to be using optimized reads. So this instance supports 230 gigabytes of tiered cache. If you want more, you choose a different sized instance. So to get the equivalent amount of memory in a cache, we would have had to use an R6G.12xlarge. Obviously, that's a lot larger than a single xlarge. Right, so what's that going to cost us? Well, the instance cost, if we choose the 12x large, that's going to be $5,830 roughly for a whole month. If we choose the GD.x large, different sizes, $583, it's 10 times less, right? So obviously, if the performance works out comparable for you, this is a much more economical option. In both cases, the storage IOs are included because we're using IO optimized, so that makes no difference. Right? And the size is the same for both, so we don't consider it as a difference. Okay? So overall, 90% cost reduction. I think that's a pretty nice technique if you're using Aurora Postgres and it fits your model. All right, so the solution to that challenge number 2, what did we do? We used IO optimized, reduced our cost by 90%, and it was easy. We just switched instance type, that was it. Okay. Right, so the developers at any company, now they need to test their work. They can't do it in production, because that's a bad idea. But they need to test it with production-like data. So up until now, they've been copying production, right? And they've been using an ETL job to do the copying, and it's complicated and it's expensive because you need to have full copies of the data. We don't want to do that anymore. Also, these developers are pretty keen, but they don't work 24 hours a day. So when they're not using the system, it's idle, it's wasting money too. And it takes time to refresh these things through that ETL job, so people don't do it too often, so you don't end up with a very accurate representation for your testing. You're just getting stale testing. It's not too good, right? So what we want is we want to reduce the storage cost and we want to reduce the compute cost by using some new technique and the creation time. Right, what are we going to do? We're going to use fast clones for Aurora here. So Aurora does this thing called fast clone, which is like a virtual copy. It uses copy on write to copy these things. We make a new volume, we don't copy the actual data bytes. It doesn't take very long and it doesn't cost you anything because we're not actually making a copy of the data, right? So you make a new volume, it just makes a few pointers, right? So what we might choose to do is we might choose to, let's say daily, you can do it whenever you like, we'll make a daily clone of this. And we'll maybe anonymize the data because that's what we need to do for testing. Okay, we'll call it a golden image. And so that is visible through a new database instance. New volume, new database instance. It's not costing you anything yet for the storage because you haven't modified it, right? You're paying for the instance, of course. Pay for what you use. And then what we can do is we can clone that thing and we'll make a test environment. And we can make another test environment, another one, as much as you want, up to a limit of 15 clones in this family. 15 fast clones in this family. Now, only when you modify the volume, those modifications, they start to add on to your storage cost bill. And any IOs, of course, if you're not using IO optimized. All right? So in our example, that deals with storage. I'm pretty happy with that. But we need to then leave the world of storage to talk about the next thing, right? To talk about compute, the problem that they have in compute. So remember the test environments thing they're trying to do. We have to find a way to give them good performance when they need it so that their tests can work properly, but not have to pay for these huge instances all the time when people are asleep or something like that. So what are we going to do? We can use Aurora Serverless here, right? Aurora Serverless is an on-demand, automatically scaling instance size. It's just like a regular instance. You choose it in the console just like a regular instance, except it's a magic one that gets big and small however it needs to, okay? So you can set the limits on it based on what you configure to tell me in this thing called an ACU, Aurora Capacity Unit. You say, Tim, I want this thing to not get smaller than this size and not get bigger than this size, but otherwise do what you think is right inside in that range, okay? And you only build for the ACUs that you're using per second, so it's pretty fine granularity. And it's by no means limited to a test workload. Here we're talking about a test load, but you're completely valid to use this in production as well. Many customers already do. And so we just announced 2 new changes in serverless in case you missed them. So serverless can now scale up to the maximum of 256 ACUs, which is twice as big as it used to be before. It's pretty large. And it can also scale right the way down to 0, or actually go to sleep and charge you nothing if you're not using it at all, okay? So we'll follow this cost example, right? So Aurora Standard, we talked about before, was the thing that's not IO optimized. In testing, we're not doing too much IO, so we're not really worried about the IO optimized part. We use Standard in this example. They have a team of 10 developers. They're doing 100 gigs of storage, 10% change rate, just like we talked about before. And by looking at their historical load patterns, they know that the instance they're using is idle for roughly half the time during a one-day shift that these developers are doing. So we'll use all of that in our maths, okay? And we'll use about an 8 ACU size workload. Seems about right for what they're doing. Cool. So the instance is going to cost us, if we do an R6G.large, the provisioned instance, about $62. If we do it with serverless, with those provisos before, that's $38. That's 38% reduction. That's pretty good. Happy with that. Now we go back to the clones thing. We remember that. We're talking about if we did it with full volume copies, we'd end up with 1,000 gigabytes. And if we did it with clones, that'd be 100 gigabytes, because we're just paying for that rate of change. That's a 90% reduction there too. And the IOs are the same for both, so we don't consider it. Cool. So how do we do? We got 90% cost reduction. And by using serverless for the test instances, we saved 38% on the compute as well. And for bonus points, right, we were able to scale down to 0, that new feature, go all the way down, and to go up to 256 really big. So if we want our testers to be able to do something really big, we can do that as well. Awesome. Backup. We'll quickly talk about backup. So Aurora provides built-in continuous backup. We're writing from that storage thing at the bottom there to S3 all the time by the storage continuously. It's not done by the DB instance, so that you don't have to factor it into your performance calculations. There's no scheduled maintenance time. It's happening all the time, and it's typically up to date within a few minutes of an active database rolling along, okay? So the backups are incremental, and they're charged based on the amount of space that you'll need to restore them at any point in time. Remember, we're having a full point in time restorability here within the backup window, that your retention window that you're asking me to do, from 1 to 35 days, same as what Penny described. Right? If you want to retain data beyond the backup retention period, you can use snapshots just like Penny described as well, same as in RDS. Right, so very similar to the way that RDS works, so I'm not going to dwell on it very much here. Cool. So you can manage this in a few different ways. The cost of a backup, you can use snapshot export to get it out to S3, same as before. You can use logical dumps. You can change your retention period, all very similar. You can reduce your volume size by doing some vacuum or something like that. All very similar to what RDS does. Because you pay for what you use. So if you don't use it, you don't pay for it. All right? So now let's consider some challenges across all the dimensions. Right? Challenge number 4, things are going great. We're going global now. So we have over on the left, we have region A, which is what we had before, and then we've just cookie-cutted the same thing over into region B so we can get some global resiliency, right? Now, you could build this yourself. You'd have to write all this software and keep it up to date yourself. So what they want to do is they want to get rid of some of that cross-region read latency. They want to maintain consistency as best they can. They don't have to want to write all this software themselves, right? So they want global resilience with low latency reads and sublinear cost for multiple regions. So how are we going to do it? We have Aurora Global Database. That gives us low RPO disaster recovery. It gives us fast local in-region reads if you configure it that way, and it can give you follow the sun. So if you have a workload that moves from, say, Sydney to the US to Europe, you can switch your writer over there and your read latency will remain low. So what we're going to do is we're going to focus on how Global Database enables fast local reads in this example, right? So at the starting point, we have our cluster on the left-hand side, the same thing we had before. And what we could do is we could just cookie cutter it over to the other side. Right? We can only do reads on this side, otherwise we'd have multi-writer and things would get very confused very quickly. We don't want to do that, right? So what we're going to do is we're going to set up Aurora Global Database. What that's going to do is that's going to read from the storage on the primary region and write into the storage on the secondary region. And Global Database will keep them all in sync. So here we've only got one region B, one global secondary, but you can have up to 5 of these things, so it gets a bit more flexible there too. And each one can have multiple read replicas inside it, like we talked about before. So you can pay for the compute and storage and the write I/O operations that you replicate, and otherwise the cost dimensions are all the same as we talked about before, just in 2 regions. All right, multiple replicas. So we do this, and what we do is we get local read latency. We get single-digit milliseconds instead of hundreds of milliseconds. We can make asymmetric clusters. We can make the primary be bigger than the secondary if we like, so we can balance that nonlinear cost. And for some pretty good bonus points, we get global DR as well, right? It doesn't just help with low latency reads. So that's pretty good. All right, last challenge. The customer has grown. This any company thing, it's growing and growing and growing. And they're thinking about, they're going to hit some of these limits that we have. We have 128 terabyte volume size, and we have the biggest G.48XL instance. It's pretty big, but it's not infinite, right? So you've got to plan for this. So they need a way to scale their storage beyond 128 terabytes, and they need a way to efficiently to scale the write throughput beyond that of a single writer without paying for a huge amount. We only want to pay for what we use, okay? How are we going to do this? Postgres Limitless Database went GA just a little while ago. So I'm just going to skim this quickly because there's a whole couple of other talks on it that you can dive into more detail on. So what this is doing automated horizontal scaling through sharding. You tell me the shard key, and I will split your database into pieces, and then I will change the size of those pieces and the number of those pieces as the database load goes up and down. All right? And the size of them I'm adjusting by using serverless technology. So those ACUs, Aurora Capacity Units, that's the thing that I use to control cost. You tell me how to do it, and I'll scale it up and down. All right? So we get distributed serverless, we get write scaling, but it's just a single database from your point of view, single endpoint and all that. You pay for what you use. All right, summary. I think we nailed it. We challenge number 5, all good. So now we reach the end of any company's journey, right? Just to sum the whole thing up, what did we do? We gave them 28% cost saving by using Aurora IO Optimized, and we gave them predictability, remember? We solved the challenge of read performance and gave them like a whole extra up to 8 times read performance by using those D instances, that optimized read feature. We solved the challenge they had with exploding costs due to testing or exploding failing tests. And gave them 90% storage cost reduction there and some compute cost reduction too by using clones. We used Aurora Global Database to have local low latency reads and some global DR. And then we saw quickly Postgres limitless database that will let you scale to petabytes of volume and millions of writes per second. Encourage you to see the other talks to learn some more about that. So finally, for all of you, any companies out there, not just pretend ones, right? We saw how optimizing cost and performance are complementary tasks. You've got to do them together. We saw some patterns here that let us do that independently or together. We saw that both Aurora and RDS share many common tools. All the performance insights and everything we saw before, they share those things. That helps you choose the right tool for the job. And Penny also helped us with what we could not see, right? With tools like CloudWatch Database Insights to guide us to where the bottlenecks are. So what we'd like to do, Penny and I, is to leave you with this mission, go home at the end of reInvent after you've had a good time, and with what you've learned here, whether you use RDS and Aurora, go forth and optimize your price and performance. You can do them both at the same time. Thanks for your time today, and some extra sessions if you're interested. Please do fill in the survey. We really are a data-driven company, and we'll use that to adjust what we're doing for you, give you the right content. Thank you.